The universe has a number for its energy, or rather the emptiness of the universe does. We have two ways of figuring out that number. One way is to look up at the sky. We watch how galaxies are moving, how fast space is expanding. Well, we do the math and we get a number. It's a very, very small number. It's almost zero, but not quite. Then we have another way of figuring out that number. This way doesn't involve looking at the sky. It involves looking down at our best theory of how the universe works on the smallest possible scales. This is quantum mechanics. We use its rules, we do the math, and we get another number. This number is not small. It is the largest, most absurdly big number that has ever appeared in physics. The problem is, these two numbers should be the same. They are supposed to be describing the exact same thing. But one is tiny and the other is gargantuan. The disagreement isn't small. It's not like one is 10 and the other is 12. The disagreement is a 1 followed by 120 zeros. That's it. That's the vacuum catastrophe. It's the biggest mistake in the history of science. It's a profound, embarrassing, and deeply exciting puzzle that sits right at the heart of modern physics. It tells us, in no uncertain terms, that we are missing something huge about how reality works. To really get what this is all about, we have to start with the vacuum itself. What is a vacuum? In everyday life, you think of it as empty space. The space between planets. The space inside a light bulb with the air sucked out. It's nothing. Emptiness. For a long time, that's what physicists thought too. But quantum mechanics changed everything. According to quantum field theory, which is our best description of particles and forces, a vacuum is not empty at all. It's not a quiet dead void. It's a seething, bubbling, chaotic mess of activity. Think of it like this. The universe is filled with fields. There's an electron field, a photon field, a field for every fundamental particle we know of. A particle, like an electron, isn't a tiny little ball. It's just a vibration, a little ripple, a concentrated bit of energy in its corresponding field. When you see a light beam, you're seeing ripples in the photon field. When you touch a table, the electrons in your hand are pushing against the electrons in the table, and those are all just ripples in the electron field. So, what is a vacuum? A vacuum is what you get when you take all the particles away. You remove all the ripples. You're left with just the fields, perfectly calm and flat. Or so you would think. But there's a rule in quantum mechanics called the Heisenberg Uncertainty Principle. It puts a fundamental limit on how much you can know about something. One version of it says you can't know both the exact position and the exact momentum of a particle at the same time. Another version says you can't know both the exact energy of a system and the exact amount of time over which you're measuring it. This principle applies to the quantum fields in a vacuum too. It means a field can never be perfectly calm. It can never have an energy of exactly zero and stay there. If it did, you would know its state perfectly, which the uncertainty principle forbids. So even in a total vacuum with no particles in it, the fields must constantly jiggle. They fluctuate. They have a minimum amount of energy that they can never get rid of. This is called the zero-point energy. Out of this jiggling, pairs of particles and antiparticles can pop into existence. They live for a tiny fraction of a second, borrow some energy from the vacuum, and then annihilate each other, paying the energy back. This happens everywhere all the time. The vacuum is a foam of these virtual particles constantly appearing and disappearing. It's the busiest place in the universe. All this activity, all this jiggling and foaming has energy. This is the vacuum energy. It's a baseline, an inherent, an intrinsic energy that space itself possesses just for existing. So, now we have two ways to approach this energy. We can look at its effects on the large-scale universe, or we can try to calculate it from our theories of the small scale. Let's start with the big stuff. Back in 1915, Albert Einstein gave us his theory of general relativity. It describes gravity. It says that massive objects warp the fabric of space-time, and this warping is what we feel as gravity. His equations worked beautifully. They described the orbit of Mercury perfectly. They predicted that light would bend around the sun, which was later confirmed. But there was a problem. His equations suggested the universe should be dynamic. It should either be expanding or contracting. At the time, everyone, including Einstein, believed the universe was static and eternal. It had always been here, and it wasn't changing. To fix this, to make his equations produce a static universe, Einstein added a new term. He called it the cosmological constant. In his equations, it was represented by the Greek letter lambda. This cosmological constant acted like a kind of anti-gravity. It was a constant energy density of space itself that would push everything apart. He could fine-tune this value to perfectly balance the inward pull of gravity from all the matter in the universe, resulting in a perfect static cosmos. A few years later, the astronomer Edwin Hubble made a shocking discovery. The universe wasn't static. He observed that distant galaxies were all moving away from us, and the farther away they were, the faster they were moving. The universe was expanding. Einstein's fudge factor, the cosmological constant, was no longer needed. The universe wasn't static after all. He reportedly called it his biggest blunder and threw it out. For most of the 20th century, physicists assumed the cosmological constant was zero. But then, in the late 1990s, something even more shocking was discovered. Astronomers were trying to measure how much the universe's expansion was slowing down. They expected it to be slowing because the gravity of all the galaxies should be pulling everything back together. But they found the opposite. The expansion of the universe is not slowing down. It's speeding up. It's accelerating. Something is pushing the universe apart. Some kind of anti-gravity force is woven into the fabric of space itself. And the simplest way to describe this in Einstein's equations is to bring back the cosmological constant. Einstein's blunder wasn't a blunder after all. This mysterious force was given a new name, dark energy. We don't know what it is, but its behavior is exactly what you'd expect from a cosmological constant. It seems to be an intrinsic energy of the vacuum, and because we can measure the rate of this accelerated expansion, we can calculate how much energy density is needed to make it happen. When we do that calculation, we get a number. The energy density of the vacuum, as observed through cosmology, is tiny. It's about 10 to the power of minus 9 joules per cubic meter. It's a positive number, but just barely. It's so small that for most of the universe's history, the pull of gravity from matter was stronger. Only in the last few billion years has this dark energy become dominant, causing the expansion to speed up. So, that's our first value, the observed value. It's a very small positive number that we get from looking at the universe. Now, for the second value, the one we get from our theories. This is where we go back to quantum field theory. You want to calculate the energy of the vacuum based on all those jiggling fields and virtual particles. The idea is simple enough. You take all the quantum fields we know about. You calculate the zero-point energy for each one. Then you add them all up. Let's just take one field, the electromagnetic field, whose particles are photons. The field can jiggle at all sorts of different frequencies, like a guitar string playing many notes at once. Each of these modes of vibration has a minimum quantum energy. To get the total vacuum energy, you have to add up the energy of all the possible modes. And here's where the calculation goes horribly wrong. How many modes are there? Well, there are modes for low frequencies, long wavelengths, and modes for high frequencies, short wavelengths. In principle, the wavelengths can get shorter and shorter, all the way down to zero. This means the frequencies can get higher and higher, all the way up to infinity. If you add up the energy from an infinite number of modes, you get an infinite amount of energy in every cubic centimeter of space. This is obviously wrong. An infinite energy density would mean an infinite gravitational pull, and the universe would have instantly collapsed into a black hole. So that can't be right. Physicists have a standard way of dealing with infinities like this. They say, okay, our theory probably breaks down at some point. It doesn't work for infinitely high energies or infinitely small distances. There must be some kind of cutoff. We should only add up the energies of the modes up to a certain maximum frequency and then stop. What's a reasonable cutoff? The most natural one is the Planck energy. This is a fundamental scale in physics where our current theories of gravity, general relativity, and quantum mechanics are expected to break down. We believe a new theory, a theory of quantum gravity, would be needed to describe what happens at this incredibly high energy. The Planck length is the smallest meaningful distance, about 10 to the power of minus 35 meters. So we'll add up all the jiggles of the quantum fields for all wavelengths down to the Planck length. This gets rid of the infinity. Now we can get a real number. So we do the calculation. We sum up the zero-point energies of all the known particle fields up to the Planck cutoff. The number that comes out is staggering. It's about 10 to the power of 112 joules per cubic meter. Now we can compare our two numbers. The observed value from the expansion of the universe is about 10 to the power of minus 9. The predicted value from our best theory of particle physics is about 10 to the power of 112. Let's be clear about the difference here. This isn't a small disagreement. It's not a rounding error. It's a mismatch of 121 orders of magnitude. It is a 1 followed by 121 zeros. To put that into perspective, this is like measuring the size of a single atom and getting an answer that is the size of the entire Milky Way galaxy. It is like carefully calculating the weight of a feather and concluding that it weighs more than all the stars in the observable universe combined. It is by far the worst theoretical prediction in the history of physics. This is the vacuum catastrophe. If the theoretical value were correct, the universe would be a very different place. The repulsive force of this enormous vacuum energy would be so strong that it would have completely overwhelmed gravity from the very first moments of the Big Bang. The universe would have expanded at an unimaginable rate. It would have ripped itself apart in a fraction of a second. Atoms could never have formed. Stars and galaxies would have been impossible. Life certainly couldn't exist. The fact that we are here in a universe with structures like galaxies and planets is proof that the real vacuum energy is tiny. Our observations are right. Our theory, or at least our calculation, must be spectacularly wrong. So what's going on? How can our best theories be this wrong about something so fundamental? This is the question that keeps physicists up at night. There are a few main ideas, but none of them are fully satisfying. One idea is that there's some unknown principle or symmetry in nature that makes all these huge energy contributions cancel out. Imagine you have a huge positive number and a huge negative number that is almost exactly the same size. When you add them together, you get a very small number. Maybe for every quantum field that contributes a large positive amount to the vacuum energy, there's another field that contributes a large negative amount. They fight each other to a near-perfect standstill, leaving only the tiny residue that we observe as dark energy. A theory called supersymmetry, or SUSY, was a leading candidate for this for a long time. In a supersymmetric universe, every known particle has a superpartner. Matter particles like electrons have force-carrying superpartners, and force-carrying particles like photons have matter-like superpartners. The nice thing about this theory is that matter particles, fermions, contribute negative energy to the vacuum, while force particles, bosons, contribute positive energy. In a world with perfect supersymmetry, the number of fermion and boson types would be exactly balanced. Their contributions to the vacuum energy would cancel out perfectly. The total vacuum energy would be exactly zero. This is very elegant, but it gives an answer of 0, and we observe a small positive value. More importantly, we've never seen any of these superpartner particles. Experiments at the Large Hadron Collider have searched for them, and they've found nothing. If supersymmetry does exist, it must be a broken symmetry. This means the superpartners must be much heavier than their regular counterparts. But as soon as you break the symmetry, the perfect cancellation is ruined, and you get a huge vacuum energy again. So while supersymmetry helps, it doesn't solve the problem on its own. Another, more controversial idea is the anthropic principle. This one steps back and looks at the problem from a different perspective. It basically says, maybe there's no deep reason why the vacuum energy is so small. Maybe it's just a lucky accident. This idea often goes hand in hand with the concept of a multiverse. Imagine there aren't just one, but countless universes, all part of a larger multiverse. In each of these universes, the laws of physics are slightly different. The vacuum energy, in particular, could take on a different random value in each one. In the vast majority of these universes, the vacuum energy would be huge, just like our theory predicts. These universes would either rip themselves apart instantly or collapse in a big crunch. They would be sterile and dead. No stars, no planets, no life. But in a very, very tiny fraction of these universes, by pure chance, the positive and negative contributions to the vacuum energy would happen to cancel out almost perfectly, leaving a tiny value like the one we see in our universe. Only in these rare, finely tuned universes would the expansion be gentle enough for galaxies and stars to form. And only in those universes could life evolve. So, of course, we find ourselves in a universe with a small vacuum energy. We couldn't exist to ask the question in any of the other kinds. We won the cosmic lottery. Many scientists are deeply uncomfortable with this explanation. It feels like giving up on finding a real, physical reason. It doesn't explain why the value is what it is, just that it has to be this way for us to be here. It's also very difficult, if not impossible, to test. You can't visit another universe to check if the vacuum energy is different there. It might be the right answer, but it's not a satisfying one for a physicist who wants to understand the fundamental machinery of reality. A third possibility is that we don't understand gravity. General relativity has passed every test we've thrown at it, but maybe it's not the complete story. Perhaps the vacuum energy is huge, just as quantum theory predicts, but it doesn't gravitate the way we think it does. Maybe gravity is somehow blind to this enormous sea of energy. There are theories of modified gravity that try to explore this. But they are very difficult to construct. It's hard to change Einstein's theory in a way that fixes the vacuum energy problem without breaking all the things that it gets right, like the orbits of planets and the bending of starlight. This leads us to the most likely and also the most difficult path forward. The problem is probably that we are trying to smash together two theories that are fundamentally incompatible. General relativity is the theory of the very big planets, stars, galaxies, the expanding universe. It's a classical theory, meaning it doesn't include the weirdness of the quantum world. The quantum field theory is the theory of the very small particles, forces, the vacuum. It doesn't include gravity. The vacuum catastrophe arises at the exact point where these two theories meet. We are using our quantum theory to calculate the energy of space, and then using our theory of gravity to determine what effect that energy should have on the universe. The spectacular failure of this calculation is a giant signpost pointing to a deep crack in the foundations of physics. What we need is a single theory that can describe both gravity and quantum mechanics. We need a theory of quantum gravity. This is the holy grail of modern theoretical physics. There are a few main contenders. String theory is one. It replaces point-like particles with tiny, vibrating strings. The different ways a string can vibrate correspond to different particles. In some versions of string theory, the huge number of possible vibrations and fields could provide a mechanism for the cancellations we need, although no one has found a definitive way to make it work yet. Another is loop quantum gravity. This theory suggests that space-time itself is not smooth and continuous, but is made of tiny, discrete chunks, or loops. If space has a minimum possible size, then there would be a maximum possible frequency for a quantum field's jiggle. This might tame the calculation from the start, avoiding the need for an artificial cutoff. But again, it's a work in progress. It's also possible the solution is something completely different, something no one has thought of yet. Maybe our understanding of what the vacuum is or what energy is just wrong. Maybe we are making a foolish assumption in our calculation that seems obvious now, but will look silly in 100 years. The vacuum catastrophe isn't just a numerical problem, it's a conceptual crisis. It tells us that our two great pillars of 20th century physics, general relativity and quantum mechanics, cannot both be completely right as they currently stand. They are like two brilliant but contradictory instruction manuals for the same universe. This might sound like a failure, but in science, a problem this big is an opportunity. It's a clue. It's a giant flashing neon sign that says your understanding is incomplete. There is something new and wonderful to be discovered here. The mismatch of 120 orders of magnitude isn't just a mistake. It's a map pointing toward where the next revolution in physics must lie. Solving. It will almost certainly require us to change our view of space, time, and energy in a fundamental way. It forces us to confront the deepest questions. What is the true nature of empty space? Why is there something rather than nothing? And why is the something from nothing so puzzlingly, precisely, and beautifully small? The vacuum catastrophe is the sound of our best theories screaming at us, and physicists are listening, trying to figure out what they're saying.